Welcome, focused learners. Listen, we are exactly 90 minutes away from glory. Today, we are laying out your absolute, foolproof game plan for exam victory. I am your host, your resident Cambridge expert, and your strategic coach. Today, we are tackling what I like to call the championship final of your exam preparation. We're looking squarely at Cambridge computer science syllabuses. I'm talking about 0478, 2210, 0417, and we're even laying down the foundational concepts for 9618. Specifically, we are mastering a topic that consistently trips up even the most dedicated, hardworking students: sound sampling and resolution. You see, sound sampling, it's not just a vocabulary word on a flashcard. It is a structural concept. Far too often, I see absolutely brilliant students falling headfirst into rote memory traps. You know the feeling, right? Memorizing textbook definitions until you're blue in the face, but then completely freezing up when faced with a real, applied exam question. Well, today, we change that. By the end of this explainer, you're going to have a rock-solid, sequence-based strategy to decode those tricky command words, structure your answers flawlessly, and secure those top marks without ever second-guessing yourself. We're literally taking the guesswork out of the examiner's mind and putting the control right back into your hands. Let's get started.
Here is the blueprint for today's masterclass. First, we'll outline the challenge, then we'll move into the 3 layers of explanation, hit the rapid method review, uncover the power of context, and finish up with an ultimate self-check.
Section 1. The challenge. Let's look closely at the rote memory trap.
Okay, let's dive into this. The rote memory trap is hands down the #1 enemy of the Cambridge computer science student. Picture this scenario. You are sitting right there in the exam hall. The clock is relentlessly ticking down, the pressure is on, and you turn the page to see a massive question about sound sampling. Your eyes instantly lock onto a familiar keyword. Maybe it's sample rate, or maybe it's resolution. Your brain lights up, you feel this huge surge of relief, and you immediately start writing down every single solitary fact you have ever memorized about that specific term. But here is the absolutely devastating reality. By doing that, you might be answering a completely different question from what the examiner actually set for you. The topic of sound sampling and resolution should never, ever be learned as an isolated definition. When you rely solely on rote memory, you end up fixating on surface features. You see the word sound, and you completely ignore the command word right next to it that is actually asking you to evaluate, or compare, or justify. You end up reciting a vocabulary list instead of solving a digital problem. And what we're looking at right now brilliantly illustrates exactly what that trap looks like in practice. Let's do a quick teardown of 2 hypothetical students, Alex and Sam, responding to a real past paper question. Explain why a musician might choose a higher sample resolution when recording a track for a CD. Let's look at Alex's answer first. Alex writes, sound sampling is measuring the amplitude of a sound wave at regular time intervals. The sample resolution is the number of bits used to record each measurement. Now on the surface, Alex has provided a perfect textbook definition. But look at all those red pen marks. Alex scores maybe 1 single mark for basic knowledge, but loses all the rest because there is absolutely no analysis here. Alex gave us raw facts, but completely ignored the context of the musician and the CD. Now let's look at Sam's answer. Sam writes, they use a higher resolution to make it sound much better and louder because there are more bits, which is good for the CD. Oh boy. Sam rushed the response. Sam missed the command word requirements entirely. Sound much better is way too vague for a computer science examiner, and saying it sounds louder is just factually incorrect when we're talking about resolution. Both of these students recognize the topic, sure, but both failed to deliver what the assessment objectives demanded. They were distracted by the key word and missed the deeper process entirely.
Section 2. 3 layers of explanation. Let's look at how concept compression leads to those top-tier answers.
So how do we fix this? How do we move from the deeply flawed answers of Alex and Sam to the perfect green-check responses that examiners absolutely love to see? We transition to the solution by moving through a highly structured journey that I call concept compression. Listen, a top-tier answer doesn't just magically happen. It is engineered. It requires you to understand a concept deeply enough to compress it into the severe constraints of a high-pressure exam environment. You cannot just regurgitate data. You have to shape it. This is exactly where we introduce the PEEL framework, tailored specifically for computer science. That stands for point, evidence, explanation, and link. But to get to a level where you can use PEEL effectively, you first have to understand the core concept across 3 distinct layers. Let's break this down layer by layer. Layer 1 is the simple explanation. Think of this as everyday language. If you can't explain sound sampling to your grandmother, you don't really understand it. In simple terms, it's just recording a human voice so a computer can play it back later. Layer 2 is the technical explanation. This is where we inject the correct subject vocabulary. Now we are leveling up and saying the analog to digital converter, or ADC, measures the amplitude of the continuous analog sound wave at regular time intervals and then encodes these measurements as binary values. But layer 3, my friends, is the exam explanation. This is where the magic happens. This is where that technical explanation is aggressively shaped into a response that scores maximum marks under severe time pressure using that Peel framework. You make your point about the ADC, you provide evidence with sample rate and resolution, you explain the impact on file size versus accuracy, and you link it directly back to the specific scenario provided in the prompt. Students so often think they know a topic when they reach layer 2, but Cambridge exams only reward layer 3. Before we continue, subscribe to our YouTube channel AC Exams at acexams_IGC to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now.
Now I want you to look at the question we have right now. What practical consequence does sound sampling have for a user, a system, or an organization? Think about this really carefully. An examiner doesn't just want to know if you can recite the definition of bit depth. They want to know if you actually understand the real-world implications. Do you realize that doubling the bit depth doubles the file size? Which means a user's smartphone might run out of storage twice as fast, or a company's database is suddenly going to require double the server capacity, or a streaming website will require significantly more bandwidth, potentially causing endless frustrating buffering for the end user. This is what it means to solve a digital problem. You must always anchor the theory to a practical, real-world consequence. If your answer is just floating out there in abstraction without impacting a user, a system, or an organization, you are leaving marks on the table.
Taking a look here, a really useful teaching discipline, and frankly, this is going to be your secret weapon, is to strictly separate description from explanation. Look at this comparison. Description tells the examiner what the device, process, or method actually is. It's safe. It's identifying that an ADC converts analog to digital. But if you only describe, your answer is incredibly shallow. Explanation, on the other hand, tells the examiner how it works and exactly why it matters. How does it work? Well, by taking discrete numerical measurements of wave amplitude. Why does it matter? Because smaller time intervals between those samples create a much closer match to the original continuous wave, which reduces quantization errors, but, and here's the kicker, at the heavy cost of storage space. Examiners expect both. If you jump straight into explanation without describing the concept first, you just sound confused. If you only describe, you artificially cap your marks. You must combine both to demonstrate true, undeniable mastery.
Section 3. The Rapid Method Review. Let's look at a repeatable system for exam success.
So, the absolutely crucial point here is that we need a repeatable system. When you are staring down a massive, multi-part, high-mark question, panic is your worst enemy. Just writing down facts in a random order, crossing your fingers and hoping one of them hits the mark scheme, that is a strategy for failure. You need a disciplined path. This framework ensures that you aren't just reacting to keywords, but rather you are systematically dismantling the question and building an airtight, examiner-friendly response. All right, let's break down this 4-step ultimate framework. Step 1. Identify the demand. Look closely at the command word. Is it asking you to describe, explain, compare, or evaluate? That changes everything. Step 2. Classify the concept. Are we talking strictly about sample rate, sample resolution, or the physical hardware itself, like the ADC? Step 3. Explain the sequence step by step. Clarity of sequence is a game changer. Do not jump backwards and forwards. The mechanism always comes first. Step 4. Connect to context. Check if the answer needs an advantage, a disadvantage, or a specific design choice justified based entirely on the scenario. Stop scrolling. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to at acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions.
Now, what's really interesting here is how we actually apply that 4-step framework in real time. I'm putting 60 seconds on our mental clock. Let's rewrite Alex and Sam's answers regarding that musician recording a CD. The flawed answer jumps all over the place. File sizes get bigger because of more bits, which means the amplitude is measured, giving higher quality sound. It mixes the mechanism and the consequence completely haphazardly. Now look at the perfect Peel-structured answer. We explain the mechanism first and then the consequence. A higher sample resolution means more bits are used to represent each individual amplitude measurement. That's our mechanism, our point, and evidence. This allows the digital representation to capture a wider dynamic range of sound, more closely matching the original continuous analog wave. There's our explanation. Consequently, the audio quality on the CD will be higher and more professional, though it will result in a significantly larger digital file size that the CD must accommodate. Boom! That's our context and consequence, our link. See the difference? Logical ordering captures maximum marks every single time.
Section 4. The power of context and real-world transfer. Let's move into our interactive workshop phase. This is where we separate the top-tier championship students from the rest of the pack. Strong exam performance depends entirely on specificity. If there's a golden rule in Cambridge computer science, it's that generic responses rarely, if ever, gain full marks. Real-world transfer matters because it converts your static memory into dynamic, exam-ready usefulness. You have to prove to the examiner that you truly understand how these abstract theories actually operate inside real machines, real networks, and real organizations. The exact same patterns behind sound sampling appear across a multitude of environments. Look at this list for our Challenge 1 data scan: phones, websites, databases, automated systems, secure systems, media handling. If an exam question is set in a retail environment where a database is storing audio clips for a store's PA system, your answer must stay inside that context. If you are discussing voice over IP for mobile phones, you must justify a lower sample rate to preserve bandwidth and reduce latency during a live call. If you are discussing high-end media handling for a streaming service, you justify higher resolution for audio fidelity, but you absolutely must acknowledge the trade-off with buffering and data transmission speeds. Applying the concept to these specific boundaries forces you to justify a choice, proving to the examiner that you understand the true engineering trade-offs of computer science.
Okay, it is time for Challenge 2, our Find the Flaw challenge. I'm giving you a 60-second visual scan in your head. Look at this incredibly flawed sample paragraph. Sound sampling creates digital files. This is an advantage for secure systems. Can you spot why this answer is just bleeding marks? I'll tell you. The student has identified a basic fact, creating digital files, and they've stated an advantage, secure systems. But there is absolutely zero connective tissue between the two. Stating an advantage with no underlying reason or technical justification loses marks every single time. To fix this, you must explain why it's an advantage. You would need to say something like, by converting analog sound into digital binary files through sampling, the audio data can now be encrypted using cryptographic algorithms, providing a clear advantage for secure systems as unauthorized interception would only yield unreadable ciphertext. You see that? You must provide the actual engineering reason the advantage exists.
Computer science reasoning becomes much stronger once boundaries are understood clearly. This right here is a foundational truth of the entire syllabus. But what do we mean by boundaries? We mean the stark, uncompromising contrasts between related concepts. You must know the boundary between memory, which is volatile RAM used for active processing, versus storage, which is the non-volatile SSD holding the sound file permanently. You must know the boundary between raw data, which is just the binary ones and zeros of the sound sample, and information, which is how the media player actually interprets that data as a song you can listen to. Right now, for Challenge 3, I want you to initiate a 30-second speed writing challenge in your mind. Craft a PL paragraph that justifies why high-resolution sound sampling requires more storage on a hard drive, not just more memory. Understanding these precise technical boundaries prevents you from using terms interchangeably, which is a massive red flag for examiners.
Section 5. The ultimate self-check. Let's do a rigorous 4-question audit.
You've seen the traps. You've learned the 3 layers of concept compression. You've mastered the rapid method review sequence, and you now completely understand the absolute necessity of context and boundaries. Now, we transition to the final system presentation. This is your ultimate cheat sheet to guarantee absolute readiness for the Cambridge Computer Science exams. Before you ever walk into that exam hall, you need a surefire way to test if your knowledge is actually durable. Here is the 4-question practical self-check. If you can answer these 4 prompts aloud, without looking at your notes, and without relying on memorized, robotic wording, your knowledge is 100% exam ready. Question 1. What is it? Can you define sound sampling clearly and simply? Question 2. How does it work? Can you explain the ADC, the amplitude, the time intervals, and the binary conversion without stumbling? Question 3. Where is it used? Can you provide a specific contextual example like a music studio or a VoIP phone call? Question 4. Why is it better or worse than an alternative in that exact situation? Can you evaluate those crucial file size versus audio fidelity trade-offs? If you hesitate or stumble on any of these 4 questions, your revision cycle isn't finished yet. You need to go back, read the foundational theory, and practice the recall again. This forces true adaptability.
And this brilliantly illustrates our complete computer science success blueprint. It is the powerhouse combination of command-word decoding, layered explanations through the PEAL framework, and logical sequencing embedded deeply in real-world context. This is your ultimate time management matrix. It stops you from overwriting on low-mark questions and under-explaining on high-mark questions. Listen to me closely. Students who implement these computer science strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder: subscribe to our YouTube channel Acing the Exams at Ace the Exams IGCSE to excel in your Cambridge examinations. Subscribe right now to Ace the Exams IGCSE and click that bell. Don't let another exam pass you by.
So I leave you with this final, provocative thought to chew on before exam day. Are you simply repeating definitions, hoping for the best, or are you actually sharpening your reasoning to command top marks? The choice is entirely yours, but you have the blueprint now. Drop a comment below with your target grade for computer science and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here.